the American Academy of Arts and Sciences, and a foreign member of the Royal Society of London. He's received the IEEE William R. Cherry Award, that's the highest award in solar cells, the Buckley Condensed Matter Prize, the Isaac Newton Medal, the Rank Prize, the Harvey Prize, the IEEE Photonics Award, and I could go on and on. But I will stop here and please ask you to help me welcome Eli to the stage and hear about deep learning, the reincarnation of analog computing.
Okay, so if you haven't noticed, Bjorn and I are the co-chairmen of the EECS Colloquium, so we'd like you to come as early and often. And I noticed a large number of people arrived right after 4. Unfortunately, they take away the cupcakes at 4. This is Pavlovian training to get you to come here early. So please come by and enjoy. We generally have great speakers, and this has been no exception the past month. Some terrific, wonderful people. Now, this talk, though, is going to be a little bit different. And the reason why it's different is we usually have we bring some real big shot in from, Google and various other places, and they tell us about the great accomplishments and so forth. Today we're going to do something a little different. I'm not going to talk about great accomplishments. Instead, here's what I'm going to do. I've noticed a new development in our field that seems to be making very extravagant claims. In fact, some of our earlier speakers this semester, we had an entrepreneur who a very serious person, but he said that his company was making accelerators for deep learning, and he stood right here and he told it, and I envy all the young people, he said, because you're at the very beginning of this, and this is going to be so big that everything up until now is going to be regarded as dumb computing, and from now on it's going to be intelligent computing. So that's a pretty extravagant claim. But it's sort of an indication that there's something bubbling up. So I wanted to brainstorm with some of the other smart people around here and see if we can get a viewpoint on what's happening. So the main thing that I see happening is that, not for the first time in my life, but for the second time in my life, analog computing has become important. Now, it was actually important when I was a child. When I was a child, I would read things, and they said, no, there's this great new thing called computing, and nobody knows how it's going to turn out. There's digital and there's analog, and nobody knows which one's going to win. Okay, and that didn't last very long. And so we know who won up until now is the digital one. But there are some new developments that I'll try to show why maybe there'll be some opportunity for analog computing. And so this, we'll see how this works out. So let me get into it. So this is not an explanation of some great achievement, but rather an exploration of what might be possible. And I think the highest thing is to predict the future accurately, of course. And so I'm not smart enough to predict the future, but maybe combined with all the smart people at Berkeley, that there is some wisdom in crowds, and especially this is a very smart crowd. So let's see if we can anticipate what's coming up. So this is the question, should we bring back analog computers? I just found this on the web. You can search. I just needed a graphic, an interesting looking graphic, that's all. Okay, now, so the reason why analog computing is coming back is that we have found that many important algorithms do not seem to require high precision. And that's what killed analog computing in the first place. You would do things with operational amplifiers, and there wasn't much accuracy in the voltage, and it was very sensitive to the initial conditions, and you just couldn't get enough bits of accuracy in analog. And of course, even in analog, we can talk about bits of accuracy, and I will do it that way. So I'll show you the algorithms that seem not to require so much precision. In particular, what has emerged is machine intelligence, optimization, deep learning, and I'll show you this has everything to do with matrix multiplication. And there's a very simple way to do analog matrix multiplication. And the simple way is you take current and multiply it by conductance. That's a multiplier. That's an analog multiplier. So you can have, as your input, you can have some conductance, and you can have some current inputs. And that's a way, and then you can build that up into a matrix, analog matrix multiplication. And it might be accurate enough, and I'll show you why in a minute. So that's one trend, and that's a pretty big trend. This whole thing is gigantic, but it's not analog. What's really happening, and I'll show you, is that there are maybe at least 100 companies, startups, in the past 2 years, 3 years maybe, that have pursued digital accelerators for deep learning. It's regarded as important enough that we have to get away from the normal architecture, and we have now new architectures for digital matrix multiplication and all the other mathematical accoutrements. But if they do it digitally, maybe we can do it analog. So that's one avenue, and it's an important one from the viewpoint of entrepreneurship. A second avenue that has emerged is not exactly simulated annealing. So simulated annealing is a way to do optimization. It goes back to the early 1980s, and it was really a style of software. What has emerged recently among certain hardware people is that, oh, I can do actual annealing. I don't have to do simulated annealing. Well, at one level, you can actually lower the temperature, and that's your annealing step. But there are other ways of emulating the lowering of temperature. And so there's a whole bunch of this, and we're beginning to witness the rise of the analog annealing machines. And you may laugh at this, but there are at least half a dozen startups dedicated to this. And yet a third approach, is, which I'll explain as we get toward the end, is adiabatic computing. And well, you know, the problem with quantum computing is they have only one algorithm. And so they've been looking for more algorithms. So they came up with quantum adiabatic computing as an algorithm. I'll explain the algorithm. But they're making some progress on it, but it actually doesn't seem to offer that much more than classical adiabatic computing. So that becomes another analog way of solving very hard problems. And these last two claim to solve NP-complete problems that are NP-complete. So that means they're hard problems. So we'll see. So first, let me describe about the deep learning. Okay, and the main thing I will be saying is that the most difficult step in deep learning involves a lot of matrix multiplication. And so let's see if we can do an analog way of doing matrix multiplication. And matrix multiplication is also valuable for optimization and for machine intelligence, many other things. So if we had an analog matrix multiplier, that's not a bad thing. So here at the EECS Colloquium, we had Andrew Ng from Bodai 3 years ago. And he told us about a surprising success in deep learning that was still in the early stages, where people were kind of dazzled by it. And the main success was they were able to come up with a piece of hardware, or an algorithm, if you like, that was able to identify images and look at an image and identify it. And so Andrew walked us through the steps of how we identify images. And by the way, I noticed there's some people standing there. I would say this talk is not going to be that good that I'd want to stand through the whole talk. So I would say there's a lot of empty seats up here. So just don't burden me with the responsibility for entertaining you while you're standing. Just come on down. Okay. Okay. All right. So how does the brain process images? They've actually investigated this. They actually gave the Nobel Prize in medicine for this. And that is that the brain first looks for edges. And indeed, in computational image processing, they look for edges. So you see here, there are a couple of edges in here. And so you do that. Okay. And then let's say you have a very complicated image like this one. You break it up into small patches. So this 14 by 14 patch is roughly about 200. You turn that into a vector of 200 elements, and you try to figure out what's going on. You look for those edges again, okay? And what you do is you try to find a matrix which, when it multiplies the vector representing the image, will project out this, oh yeah, that's an edge. And so it's not too hard to come up with such a matrix. And then what you do is, having broken up the image into all these little pieces, you start looking for all the little edges that might appear in each little image. And you build up from all those little edges. And so you can break it up into fundamental elements. And so basically, the mathematical part here is that you regard the vector, the image, as being kind of a very long vector, and with it, and that vector, if it happens to be an edge or something interesting, you can just using linear algebra, you can project out that particular property of that vector by essentially an inner product. So you can train matrices that will project out things that you're interested in, like edges. Then what you can do is then you say, well, you notice you start with the pixels, and then you say, oh, there's a bunch of edges in there. And then you say, well, edge doesn't really tell me very much. Let me put a few edges together, and I can make more complicated parts. And so these parts look kind of odd. But then you can put those parts together, project them out, and these ends up looking a little bit more like faces. And so you've taken a step toward recognizing people's faces. And this is the so-called deep part of deep learning, is that you do it in layers like this. And in these layers, you build up a projection that says, yes, I project out a face from that very long vector. So that's how they do it. Now, the projection is essentially linear algebra. That is to say, you're trying to identify some part of your vector that matches what you're expecting, and so you take the image you start with, and you filter it, and maybe you have filtered it down to edges. So maybe this is just the edges. And then you then do linear algebra on those, and you project those out to more complicated things. And then those more complicated things, finally, you're projecting out a person's face, and maybe even you're projecting out who it is. And finally, after these matrix operations, you get a 1. Let's say in the first element of the vector, it's a 1 if it's someone you know, and it's a 0 if it's someone you don't know. So this is the level at which they do it. And there is a huge number, there are a huge number of matrix operations, and each matrix is at a higher and higher abstraction level. So it's a more complicated superposition of edges. By the time you're here, you're superposing edges. By the time you're here, you're superposing fractions of people's faces, and finally you're getting faces. And so each step involves matrix algebra. And then there's a learning phase where you run everything backwards. So you find, of course, when you first do it, it's erroneous. You get an error. And so there's some matrix algebra. I'll show it to you in a minute, but this is sort of an indication of what they can do. And this is Andrew Ng, who was our speaker here, and he became famous for finding cats in the YouTube database of images. So he was working at Google at the time, and he had access to things that nobody ever had before, which is, of course, a lot of computing power with the big budget of Google, but he also had access to the YouTube database, where he could train the database and say, yes, that's a cat. And with the training, you say, oh, well, my matrices didn't work. I've got to change my matrices so they'll properly project out cats. So the promise of that, well, this is an example of the promise. And they already have things, for example, I've tried this in a foreign country, is I look with my cell phone, and I'm looking at a street sign. I can't tell because it's written in a foreign language, and I look at it, and it reads it out to me. I actually see the words in English. Okay, and that you already have. But imagine I was doing this, and I was in in a beautiful place, but not a botanical garden. See, botanical gardens, they identify what you're looking at. But let's say you're out in the wild, and here's my cell phone, and I'm not even taking a picture. I'm just looking at the flower, and it tells me exactly what type of, it names the flower because it recognizes it. So this is an example of what will be possible. So the key is linear algebra, and linear algebra is also the key toward optimization. Essentially, you're optimizing the weights in the matrix. So you have a merit function is what you thought it was and what it actually was. And maybe you thought it was a cat, but it wasn't. And so there's an error, and you take the mean squared, and you try to minimize the mean square error. And you have a series of matrix operations, which are a little complicated to get into, but it's very powerful stuff, and it is useful in all areas of optimization, not just for recognizing images, but all general optimization problems even in mechanical engineering and in other parts of engineering. And there's very beautiful linear algebra. And what we're trying to do is optimize the matrix so it projects out correctly that you were looking at what you thought you were looking at. And at the end, it's all about these matrix vector products. So you can do this in both directions, both in so let me tell you about the two directions. There's the inference direction where you're trying to figure out, you're trying to project out to identify what image you looked at, but there's the training direction as well. And the training direction is called backpropagation, and the forward direction is called inference. So I might use those terms. So I have a little bit of experience using this very fancy linear algebra because in my group we do optimization of electromagnetics problems. So here's a problem in electromagnetics. You have a light wave going in silicon photonics, and you want to make a splitter. So it splits equally, but you don't want to scatter radiation and lose it. You want it to be a very efficient splitter. And so what we do is we go through a lot of this fancy linear algebra, and whereas when we started, maybe we had 71% efficiency, but then after 30 iterations, with each iteration, there's a whole bunch of matrix algebra, and finally we get 98.9% efficiency of coupling into the two waveguides. And of course, as we go through the iterations, we follow the merit function on up, and the merit function is just how efficient we were, and it's very close to 100%. So it's used in all areas of engineering. Now, how was this originally done? It was done at Google with extremely large arrays of computers, 16,000 CPUs, but that's not how they measure the quality of their system. They measure it not by the number of processors, but by the number of available connections. And so the figure of merit in their business is how many connections do you have? So it's all about communication between the CPUs, and that the interconnect count is actually more important than this CPU count. That was kind of interesting. Now, what is the low-hanging fruit of deep learning is recognizing images, which I already talked about, but you can also recognize speech, you can translate speech, and you can also recognize text, maybe the meaning of sentences. That seems a little hard, but this is just the beginning. There are a huge number of things that you can look for. I saw a paper analyzing the crime statistics in Los Angeles, factoring in the calendar, but also factoring in what the weather was, and trying to predict where the next crime is going to be. So it's everywhere. It's not just for the obvious things like recognizing images. Okay, so I already indicated what changed since the 1950s is huge computational power and huge training sets, and this has now become very successful, but it required very large CPUs. This is the status as of 3 years ago. Then they said, oh, wait a minute, this CPU is just doing linear algebra. There's a better way to do linear algebra, is to use a graphics processing unit. And so NVIDIA became the darling of Wall Street because they're offering artificial intelligence. That sounds pretty good. And the GPUs started replacing the CPU. So nobody does it that way with a huge investment in CPUs. They have accelerators. This is the beginning of the accelerators. And the basic point about the accelerator is you can do linear algebra more quickly. And so starting about 3 years ago, people noticed, wow, this is a big thing. This is neural networks. It's artificial intelligence. It's very, very promising. It's very different from all the computing we've had up to now. So many startups emerged, and Professor Jan Rabai assured me there were at least 100 startups in this field of accelerators for deep learning. So I went online and I tried to look up the logos, and it's very interesting to see these, because each of these logos is representing some artist, but it's also representing the hopes of a group of engineers that think that they're smarter than all the 99 other companies that are in this field. But some of them undoubtedly will be successful. We had, for example, one of our speakers about a month ago was this company, GraphCore. And so it just goes on and on. More of these rather artistic logos here. This one is regarded as more serious in this field, but they all have their hopes. Okay, and it's all about, look at they all have their slogans too. The artificial intelligence era has arrived, and we're making coprocessors that say the deep learning accelerators. It's based on biology, etc. And let's just go back. What were some of the leader of embedded artificial intelligence? Create something different. I don't know. That doesn't sound that great, but it's a compute appliance. It's not a computing appliance. It's a compute appliance that redefines how machine learning is done. Okay, so they all have their hopes, but the big companies are not to be left behind. Intel could not afford not to be in this space. So they acquired no less than 3 of these startups. So they paid cash for 3 of these startups, which is kind of interesting. And we had, as a speaker at the E3S Colloquium a few weeks ago, we had the representative of Nirvana. And of course, since they were bought by Intel 12 months ago, they have to have an Intel. So next level computing powered by Intel. Okay. And powering the machine intelligence revolution. But they're all absorbed into Intel. And of course, it's great for autonomous driving because you get to interpret the images. You look around you and you can actually understand what you're seeing. So this startup is dedicating itself to advanced driver assistance systems, or in other words, autonomous driving. Now, Google is not to be left behind. They weren't going to let NVIDIA take over this business with their graphics processing units. So we heard a talk here at the EECS Colloquium last spring from our own Dave Patterson, but he is now not a Google employee, I should say. He's a Google employee. And how important is this? Well, he described himself, he's now a hardware guy. Okay, and he came and he told us about the Google hardware, which is the tensor processing unit. So you see the progression, CPU, GPU, TPU, everybody's got to be in this. Okay, now, how important is this? Well, we had an interesting Labor Day weekend. The faculty were exchanging emails about Putin's comment. And now this comment was published in the Russian press. It was actually a message from the president to all the starting school students that they should do a good job in school, okay? And one of the things he said is that, well, I'm pretty sure, I mean, if you're the president of Russia, you don't actually write these messages. You have someone who works for you who writes these messages. But whoever was working for him was trying to curry favor with him. You can tell by the quotation. He says, first of all, artificial intelligence is the future of all mankind. And then the person who wrote this for him, the staff member, said, whoever becomes a leader in this sphere will become the ruler of the world. And I would say that person was looking for more funding. Okay, so that's kind of interesting. So it has been noticed at the higher political echelons. Now, so what's going on? What was Google? What were they doing? Well, they had the TPU accelerator, and what was the big secret? I actually tried to get Patterson to speak to us early. He said he'd come much earlier than when he came, but they hadn't put out the press release yet. So they were keeping it very, very secret. So finally, they gave out the press release, and he was able to come and talk to us. And so what was the big secret? Well, the big secret was they went from normal floating point to half precision, which is 16 bits. And then a few months later, they came out with a new big secret, and that is they went to quarter precision, 8 bits. Okay? So 8 bits, 8-bit precision, that's not much. I mean, that's like 0.5% accuracy. I could almost do that with analog. So that's something to be concerned about. That's the big breakthrough, is they're just reducing the number of bits of precision. Hey, there's a lot of ways of doing that. Well, in the past 18 months, a series of papers have appeared that indicate, 8 bits, that's much more than what we need. And so I'll show you a paper saying that 4 bits are sufficient, another one that 2 bits are sufficient, and then maybe even 1 bit is sufficient. So apparently, in the inference direction, in forward inference, you don't need that much accuracy. Now, is that because images are so grossly overdetermined? There's a huge amount of data in images, far more than maybe we need. I don't know, but they have demonstrated this. So here's a paper, conference paper here. I'm not even familiar with this conference, but it says 4 bits are sufficient, okay? And this was from Intel Labs, China. So you see all the industrial people are getting into this. Okay, and then a paper appeared. This one is in the archive, and it says 2 bits are sufficient. And then another paper appeared last year and says 1 bit binary is sufficient, but with some difficulty. And this was regarded as such a great idea that Paul Allen of Microsoft funded them. Okay, so there are pretty smart people who think that this is a good area to get into. But all of those 100 startups that I showed you, they're all doing digital accelerators. None of them are doing analog accelerators. So, and all of these papers looked at it as a digital problem. So let me summarize that low precision requirement has been proven in the inference direction, but the belief is that back propagation, the learning phase, probably still requires high precision. But I question even that, but it has not been necessarily proven out. So let's just say we're just going to do this in the forward direction. We'll have an analog matrix multiplier that will give us inference in the forward direction, and we're going to look at people, we'll know who they are. We'll look at flowers, we'll know what kind of flower it is, and so on. Now, so it suggests a model where you do the training, which is kind of hard to do. It may require a lot of precision. You do it once at a central location, and then you distribute the weights, which are essentially all those matrix elements. You distribute them to millions of clients. So in effect, everybody can have an analog artificial intelligence accelerator in their phone, and it would just every now and then would get updated with new weights, and I'll be able to use my cell phone for speech recognition, image recognition, text interpretation, because it's going to be analog, it's going to take almost no power, it's going to be almost instantaneous, et cetera, et cetera. So that's the possible hope. So for that hope, we recognize where we are. Digital is still king. And so I'm forecasting a possible technological competition between analog and digital. And so digital has gone this way. CPU, GPU, TPU, and all those startups, they're doing IPU, which they call their product Intelligent Processing Unit. But the precision requirements seem to be low enough that maybe you can get what you need by analog processing, namely matrix multiplication. So let me talk about analog ways of doing matrix multiplication. So I notice I have some people who are interested in optics, so they should pay attention now. In optics, actually it says doesn't only belong to optics, but we have splitters. A splitter takes 2 inputs and has 2 outputs. So it's a 2 by 2 matrix operation. Splitter, instantaneously, you send voltages in, you get voltages out. It is a 2 by 2 matrix operation. But it was proven about 20 years ago that if you put many splitters together, and they had in mind optical splitters, beam splitters, and if you put a great many of them together, you can do any arbitrary unitary operation, which is which was very, I remember seeing that come out, and I thought, wow, that's amazing. That's got to be useful for something. Okay, so you can realize any unitary operator. So what happened about 6 months ago, MIT publishes an accelerator, an analog accelerator using silicon photonics. And it basically consists of all these beam splitters. This is sort of the symbol of a beam splitter. 2 inputs and 2 outputs. It's a little complicated to explain what's going on in here. But they put this forward as a way, this is sort of more of a picture, more of a photograph of what it looks like. But you can do these matrix operations with an array of beam splitters. Now these beam splitters, of course, they're nanophotonics, so they're very small, but they're nowhere near small enough to do a really big matrix. But it was an interesting idea. So let's go on to a different type of analog matrix multiplier. And people talk about memory has to be integrated with logic, so there's a way to do that that is very attractive and that people have been working on, and that is a crossbar resistor array. So you have crossbars, so there's wires going across and going the other way, and then at each crossing point you connect them with a resistor. And I don't know why they're not using the normal. I think I know why it's not a normal resistor, because it's an adjustable resistor. These would become then the matrix elements. So the operation would be a vector comes in on these wires, and then it gets multiplied by the matrix weights according to the resistance values, and coming out here is one column of the resultant matrix. So this is an analog way of doing matrix multiplication. It's the conductance of the resistors times the applied current, and effectively that Ohm's law is your multiplication operation. And it is nice. You get your logic together with your storage, and moreover, you don't have to waste a lot of energy calling up the information from some place where you're storing it. Then in fact, it's all stored in the processor itself in these resistors. So by the way, I got these slides from somebody at Sandia Labs. So there is.
I think that's where you're wrong. Right? I mean, the whole energy consumption in these neural networks is swapping all the coefficients back and forth out of.
That's what I'm saying is that.
Memory, and that's not gonna,
No.
You're not going to get around that.
No. It's the idea is to store the information in these weights.
The density.
Well, why don't you let me present it? This is supposed to be speculative.
It's supposed to be a brainstorming session.
Right, okay. Well, let me go out, and this is, I'm presenting not my work. I'm presenting other people's work. If you want to criticize, I might join you. Okay? So you can, they've investigated this. You can do parallel reads and writes. It's kind of nice. It does have that efficiency. They've analyzed it in a way that they see an advantage over the normal way of doing things. And so what will the crossbars be? So people get very excited. And I'll tell you who's really interested in this. Let's say somebody is working on some storage technology. Say, well, I don't have any customers for my storage technology. I know. I'll make a resistor crossbar and we'll use it for neural networks. Okay? So the people who are doing resistive RAM, they say they want to do neural networks. And we have Stan Williams at HP, and he wants to do memristors. And other people want to do magnetoresistors and so on and so forth. But there is sort of an obvious way to approach this, and that is take your flash memory and instead of running it in digital mode, run it in analog mode. So you can maybe imagine making this whole crossbar array where the resistors are all flash memory. So this is what they are promising. So I already said this, that you can distribute the weights, so you could have your flash memory gets updated once a month with the latest new flowers or people. Now, of course, the Department of Defense, we're entering a world, I mean, this is definitely coming, digital or analog, it doesn't matter. We're entering a world where they could put a camera at the entrance to an athletic stadium, and they could identify every person entering the stadium, which is kind of a shocking thing. So that's the question. This is definitely a big thing, but is analog going to have a chance? And I've given you some examples of analog. And digital, of course, is harder to work with all these PUs, TPUs, IPUs, etc. Okay, so that's all I'm going to say about the deep learning. There's an opportunity there. There are startup companies. But let me indicate two other ways to do interesting things in analog. Okay, now one of them has to do with simulated annealing. Now it's a software style, and what it means is, let's say you're trying to optimize something. So you're trying to go down to, let's say, a low energy state, but the space is so complicated. There's so many states, you couldn't possibly check them all. And so what you do is you do something, what might be called digital annealing. Digital annealing, your system might be here. You give it a little bit of thermal energy, it jumps out and keeps exploring. It jumps and jumps, and finally it ends up with some probability in the lowest energy state. And then after you gradually lower the temperature. That's what the meaning of annealing is in material science. You gradually lower the temperature, and it finds itself finally sitting in this lowest energy state. But right now, this is a style of software. It is not actually done in hardware. So what is emerging now that I can detect is that people are putting forward physical machines that actually do a kind of a physical annealing process. And so mostly they're trying to solve this problem. It's a very famous problem in physics. It's called the icing problem. And it can be expressed very simply. You have an array of spins, which are essentially little magnets, and the magnets are interacting. And they're interacting in such a way that some will be up and some will be down, and you don't know exactly which combination of up and downs has the lowest energy state. And it's really hard to find, and it's regarded as an NP-complete problem, because the only way to find out is to test every possible configuration of the spins to find out which one might have the lowest energy. So this is very interesting. And this is the regular, this is what you might think you might do physically, is just lower the temperature. But nobody ever does it that way. And I'll show you how they plan to do it. So here is the Hamiltonian. This is just telling you what the energy is, and it's mostly has to do with interactions between spins. Some of them should be up, some of them should be down. And it's a hard problem. And why is the icing problem interesting, and why do so many computer scientists pursue it? It's because many important things in computer science can be framed as icing problems, including planning, scheduling, like the traveling salesman problem, optimizing a financial portfolio, how proteins might fold, various problems in graph theory, and so on. And even when they get very extravagant, they claim that might be able to design materials. That one I really doubt. Okay, so that's a lot of promises. Okay, and so this is sort of an example of what they have. Is you have all these spins, and they interact, but they interact everywhere. There's sort of an edge to a graph. They interact, so they interact this way, and you can figure out from this what cross terms or what interactions are non-zero. So you can't quite see the numbers; they're very small, but they're numbered 1 to 8, and obviously the nearest neighbors interact, but also the one right across interacts, and so you get this funny structure to the interactions. And so finally, you let it evolve, and you start with all the spins up, and that's no good. That has a high energy, and then they start exploring around. They start flipping around, and finally they arrive at the lowest energy state, and where some are up and some are down. Now with these 8 spins, it is very easy to figure out what the lowest energy state is. So this is an example of what they're trying to solve. So the basic idea is that instead of lowering the temperature as in thermal annealing, what you do is you make an array of bistable oscillators. So you have a bistable array, and they don't quite want to oscillate. So you turn up the gain and turn up the gain, and just at the edge of oscillation, it is forced to oscillate in the mode that has the highest gain. And that's like the state that had the lowest energy. So instead of lowering the temperature, they do it kind of in reverse. They crank up the gain just until the oscillators just barely begin to oscillate, and then they fall into their bistable array, and it becomes just bistable, just like the magnets are bistable. Okay, so I'm going to show you some examples that have emerged in the past couple of years of people who were claiming to do this. Now, the oscillator that has received the most attention is called an optical parametric oscillator, but just think of it as a complicated type of laser that has instead of having simple gain, it has phase-sensitive gain. So that's all it is. And so you can imagine that you have many modes in a cavity, and lasers are notorious for being multi-mode, and it's going to pick some mode, and it's going to pick up the mode that has the highest gain. And so the first one that lasers, it'll have a threshold like every laser, and the first thing that lasers is the mode that has the highest gain. And so that is actually what's happening. Now, unfortunately, the person who was doing this, the leader of that group, is at Stanford, Professor Yamamoto. He is totally enamored of quantum, because he said if it's not quantum, he doesn't want to do it. So he sort of convinced himself that this was quantum. But actually, it's classical, and it's already interesting that it's classical. So the people who work for him, they tell me the truth. They agree it's classical. Okay, so the optical parametric oscillators, they are sort of phase sensitive, so they're bistable with respect to phase. You can get gain here at 0 phase, or you can get gain at pi phase, and either one might lase, and you have a bunch of them that are coupled, and so you have your coupled bistable oscillators, and you creep up on to the lasing condition, you creep up from below, and eventually you fall into one state, and that state is the one that had the highest gain or had the most favorable energy. And so they've done this now. They demonstrated it. It was about 16 spins. They had 16 electromagnetic modes. Obviously, that's not that big, but it's a principle that they're proving. So say, well, okay, but you look at it, and even the people who work in this group, they agree it's classical. So what happened is that Professor Jajit Chowdhury, I hope you're in the room here somewhere, Jajit, and in your group, Tianqi Wang, got onto this and said, well, I don't need to make this optical thing. I can just make electrical oscillators, okay? And I could make them bistable, and put them together into a circuit, and this circuit would explore the icing problem for at least the amount of number of circuit elements he has, and he could easily have 16 or more, or maybe even a very large number of circuit elements. And in this way, you gradually turn up the gain, then it finally oscillates, and then you measure what phase each oscillator was oscillating in, and that's the answer that is supposed to be the answer to the optimization problem. So that's an example. Okay, and there's even a version of this that where you don't do it analog, you do it digitally, but you have on a graph you have digital processors, and they're emulating this whole idea of simulated annealing. So even that has been done. But that is too digital for this talk, so let's skip that. So what I'm going to say then, and this is sort of an introduction, is that it seems like classical adiabatic computing does solve the icing problem, and it looks like it has potential, and it's simpler, and it doesn't require lasers. And everyone working on it is in the quantum field, and they're very excited. They call this quantum adiabatic computing. And so it led to a problem. So here was the problem. There's a company in Vancouver, British Columbia, called D-Wave, that is venture funded. I don't know how they managed, but they were going to promise to build a quantum computer. And then they made a public announcement about 3 years ago, we have built a quantum computer. And this was, of course, very shocking, surprising, because it was supposed to be too hard. Well, it wasn't, so the answer was it wasn't a real quantum computer. So our own Professor Umesh Vazirani, he writes a paper, How Quantum Is It Really? And of course, at the end, you can tell what that, he means it ain't quantum, okay? And, but this, it claims to do optimization problems. It is essentially following the adiabatic algorithm. It follows what I showed you is, oh, I haven't shown you the algorithm yet. Yeah, I've shown you simulated annealing, the algorithm that's coming up yet. But there's great interest in companies. So Toyota has gone into some type of collaboration with them and to solve complex optimization problems. Kind of interesting. But Umesh has his doubts. So let's see what's going on. So the this is called the, I don't know what to call it. I hesitate to use the word algorithm, but it's an adiabatic procedure. So let me tell you what is the procedure for solving the problem. You start off with a very simple problem. There are no interactions, and all the spins want to point up. Then you know the solution. They're all pointing up. Okay? And then gradually you turn on the interactions. And as soon as you turn on the interactions, it becomes a hard problem, because the icing problem is very hard. You need interactions between spins. That's the essence. And finally, after you turn on the interactions, you get a bunch. Some spins are up, some are down, and this reads out as a digital number that represents the solution to the icing problem, which can do optimization. So let me show you what the trick is. Suppose you had an LC circuit. This is why it's not quantum mechanical, because I can do it with an LC circuit. So you have an LC circuit with a lot of inductors and capacitors. They're going to have many resonant frequencies. And let's say one of the inductors, you start tuning it on the horizontal axis, and as a result of tuning the inductor, one of the resonant frequencies goes down, but the other one is hardly affected. Okay? And so, okay, well, I've made circuits like that, you know. But I've also had the other experience. When I try to make circuits like that, I often try to get two resonant frequencies to be exactly the same. And I challenge you to do that, because you can't. What's going to happen is that every time you try to make the two frequencies exactly the same, there's an avoided crossing. Now, these avoided crossings are taught in quantum mechanics. But they're not part of quantum mechanics, not really, because we get avoided crossings in LC circuits. So we can do that. We're electrical engineers. We can do LC circuits. So you get an avoided crossing. Now, something interesting happens with the avoided crossing. Let's say I was in the lowest frequency state, and I want to find the mode that, after I turn on the interactions, it still has the lowest frequency state. If I turn on the interactions very, very slowly, it goes across, avoids the other one, and the lowest frequency state is always the lowest frequency state if I turn on the interactions adiabatically. And so this is the claim. If you do things slowly, you will end up starting from a solution you had back here to a solution that you didn't have because it was hard. Here it was hard, but it's okay. You've solved it by having this analog machine made up of L's and C's that basically take you from something that you can solve to something that was really hard to solve, and then you just do it. You turn on the interactions very slowly, and there are theorems that have been proven how slowly you have to do it. So this adiabatic algorithm is highly respected among the people who do rigorous proofs, because they say, I can prove that if you go slowly enough, I will get the answer to the icing problem. So that's the trick for solving it. And so I discussed this with Umesh yesterday, and Umesh said, well, I already published this in 2014, that this is not a quantum computer, but he said even better, it doesn't have to be a quantum computer, because actually it's a great algorithm. It's a great way to do things. The adiabatic algorithm is wonderful, and it doesn't require quantum mechanics. So, wow, that's an interesting claim, and it's, as I indicated, it's not that hard to make, because you can make it with any number of bistable systems, or even just systems with inductors and capacitors and so on. So there are a great many ways of doing that. So that was my third method. So let me review the methods. I can do analog matrix multiplication, and there seems to be a demand for matrix multiplication efficiently. I can do simulated annealing for those who are interested in simulated annealing. And if you're not, if not, then maybe you're interested in analog adiabatic solutions. I have 3 different approaches for bringing analog back into computer science. So it seems to me maybe one of them is wrong or 2 of them wrong, but maybe the third one is right. Now, all I need is one great example where analog is back into computer science, and that's pretty big, because it is really revolutionary. It undoes what happened 70 years ago. So the possibility of analog coming back is a sort of a recognition that many optimization problems do not require high precision. We can argue why that is. That matrix multiplication and also easy access to storage is the key to neural networks, deep learning, optimization, all those things. But if you say, well, maybe you don't like that one, so then you want to do simulated annealing, no problem. Build an array of analog oscillators and gradually turn up the gain on these oscillators so they lock into a preferred configuration. Choose your oscillator. Optical parametric oscillators, if you like those. Subthreshold lasers, you can make an array of subthreshold lasers, and they famously lock into some complicated mode that nobody wants. But that could be a solution to an icing problem. Or make an array of LC circuits with bistable op-amps in them. All of them seem to be capable of doing physical annealing. It's similar but not exactly the same as thermal annealing. Or if none of those appeals to you, then you have the whole field of quantum adiabatic computing, but unfortunately, well, first of all, it seems like it's no better than classical adiabatic computing, but they have given it a very unfortunate name. And the name, they call this quantum annealing, which makes it look like this stuff. And it's different because it's adiabatic. It's really quite different. So this is sort of an indication, I think, that we should start to take analog computing seriously. We should talk among ourselves. We should maybe do some brainstorming. And maybe this becomes the next big thing. Okay, so I have one final slide. What's the future? What does the future hold? I see a competition, a rivalry between analog and digital, and I believe we are now seeing the door opening to that. So thank you for listening.
Right, we have some time for questions. If you have a question, please raise your hand and I'll bring the mic to you.
So if I give up on precision, digital computing becomes extremely energy efficient.
Yes, that's a good point.
So how do you compete with that?
Well, that was the last sentence on this slide. The classical digital alternatives also benefit when precision requirements are lowered. So it's going to be a tough competition.
So I think this will just support your point, but one of the companies you named, Mythic AI, one of the deep learning accelerator companies, is using analog.
Oh, there is, one of them is analog.
At least one, but I know of one.
Okay, and what is the name of that company again?
Mythic AI. It was on your slides.
It was on the slides, okay. Let's go back. Go ahead, ask the question. I'm just looking.
So, as far as we know, the synapses in the human brain are analog elements. And so I think we have very good proof of concept that analog computers do indeed really work. And so all of these schemes are very promising. But what you have to do is find the physical equivalent of the synapse in the human brain, make it small enough, make it updatable, and make it energy efficient to the same degree. And I think most of these solutions are nice if you only have a few thousand in the big lab, but to scale it down to where we have the same density as in human brain will be the real challenge in the end.
Just Koitzer, was this company?
Yep.
Interesting. So let me address your question. The pioneers, the people who kept the flame going for the past 60 or 70 years, were people who were inspired by biology. That to them, the greatest mystery was the human mind, and that the reason to build this hardware is to get insights into biology. And so those people deserve a lot of credit because they kept the field going when it sort of maybe went through multi-decade periods where it had fallen out of favor. But I think the situation has changed now. While we can respect them as the pioneers, people said, well, people are now saying, well, it may or may not be the same as what happens in the human brain, but nonetheless, it's a system that works. And now it's less important to the engineers. It's less important whether it's an accurate representation of the brain. It's now just a normal part of engineering. And we always ask, will it get the job done? Will it work? And so that emphasis has changed. So now it's not so much that we are trying to mimic the brain anymore. We just want to develop this field and see how well we can do. It's being done digitally. Of course, there's an existence proof is that you can do things analog as well. So that's a very good point.
When the founder of Nirvana took CS267 a few years ago, he learned.
Yeah, I understand he was your student. That's right. So let's get Nirvana on the screen here. Hold on.
He learned about a new matrix multiply algorithm that we had that sort of hit a energy lower bound, and so it'd be interesting to know if there's a similar energy model for the analog case that you can prove something about.
Yeah. So so you bragged about one of your former students. So my former student is at Sandia, and he is this is his project. He's sort of the analytical person behind the Sandia effort on these resistive crossbar arrays. Yeah, we need proofs, we need more information. We need to answer Chris Biester's question, is that in the end, can we get by and not be hung up on extraneous things like moving the data around?
Yeah, in the early 1990s, Paul Gray, his stump speech as digital was really starting to take over, he visioned the world like an egg, and all the stuff inside the egg was digital, and there was this thin shell between the real world and the digital, which was where analog could survive.
Yeah.
And I think if you really want to have analog computing in a practical way, making the shell thicker is a way to go. So basically doing computation in or out, and that also helps Chris's question, where the data is naturally flowing in. And I mean, just from the circuits I worked on in the 1980s, when I see new references to them, I see who's referencing this paper 40 years later. That's usually how it's being used.
I think you're right. This whole idea of requiring less precision means it's more digital right away. And so if we just start to see some encroachments where as you say, you make the shell thicker. So some specialized functions, it was better to do analog. And then maybe the shell will get to be very thick, maybe it revolutionizes everything. So we had the CTO of GraphCore here, and he was the guy who said that he envies all the students because they're not going to have to bother with all the dumb computing that came before. And so if it's that big, all you need is get a little wedge in it.
Could you talk about time performance, say in the beam splitter situation? How many multiplications per second can you pump through?
Right. Okay. So that's a really good question, and that's where the big advantage of analog is, because you just send the voltage in as quickly as the voltage can cross over a wire. You're done. Okay. And so it promises, the analog forms of matrix multiplication promise to be incredibly fast. And so that's one of their advantages.
But the adiabatic processes are pretty slow, isn't it?
Yes, that was just for matrix multiplication. The adiabatic processes are very slow. And so I'll tell you what people tell me. I tell them the same thing, okay? Let me get to the adiabatic part here. So here's they give a very unsatisfactory answer to this. Let's get to the adiabatic part. Yes, here we go. We're okay with Umesh here. Okay, so you have to go very slowly. Oh, why do you have to go slowly? It's because you have these avoided crossings, and you can't go fast through an avoided crossing. You got to go slow. That makes it adiabatic. The people who are doing this, I tell them what you just said, and here's the answer they tell me. And they say, oh, of course, if I was aiming for the absolute lowest energy state, the solution to the NP-complete problem, I would have to go very, very slow. But I'm not really aiming for the ultimate NP-complete solution. A lot in optimization, in control theory, and so on, a quick, approximate solution is also okay. And so that's the rationale that they give back to me. But I find that to be, and then that says, oh, you mean you're not solving an NP-complete problem. So it's not as exciting as what you're claiming. So we'll have to wait and see how that straightens itself out.
Any more questions? Going once? Okay, well then let's thank Eli again. And hope to see you again soon here.